Hi, everyone. Today we're going to start Chapter 10b by focusing on something called the ratio test. However, before we get to that, let's talk about Chapter 10b in general. We are focusing on the idea of converging series. So if you recall, a couple chapters ago, we talked about whether an integral can converge, and we used things like the p-test. This chapter is kind of similar to that, except we're going to be talking about whether a series can converge. And so we're going to start with the opener, part B here, because we're going to start with the type of series that you should have a lot of familiarity with, which is the geometric series, right? Because every term is multiplied by another r, which stands for the common ratio, right? And so if I wanted to write this, I can write it in summation notation, n equals 0 to infinity, a sub 1 times r to the nth power. So this is just in general, right, the explicit formula for a geometric sequence, right, except we're adding them all up. So what is all of this going to add up to, right? Well, we have a formula, a sub 1 over 1 minus r, the sum of an infinite geometric series. But remember that this only works when r is between 1 and negative 1. Okay, and so if we go back now to opener A, we have the series 2 plus 1 plus a half plus a fourth plus an eighth plus dot dot dot, the 16th, the 32nd, etc. Right? We can see we're multiplying each term by a half. And so the first thing, just something that we're going to have to do a lot in this chapter, let's go ahead and write this in summation notation. And so we get from 0 to infinity, a sub 1 is 2, r is a half to the nth power. And so because r here is between 1 and negative 1, we can use our formula 2 over 1 minus r. And so we get 2 over a half, which is 4. And let's look at C, though. This is where things get interesting in this chapter. So far, everything we talked about is review stuff, right? How about this series? What's going on here? So 1 to a half, okay, multiply by a half to a sixth, okay, I would multiply by a third. A 6 to a 24th, I would multiply by a fourth, etc., etc. And the first thing to notice here is that this is not geometric. So how can we tell if this series will converge? So we'll come back to that, but real quick, what is this series in summation notation? Hopefully you recognize these denominators as 2 factorial, 3 factorial, 4 factorial, 5 factorial, 6 factorial, right? And so we can say that this is from 1 to infinity of 1 over n factorial, okay? So if we have a geometric series, really easy to tell if it converges or not. But again, what do we do if the series is not geometric? And so this is one of our new things for this chapter, something called the ratio test. Okay, so ratio test says let the sum from 0 to infinity of all of the terms of a sub n be a series such that, and so what we're going to do, here is what the ratio test says, right? It's called ratio. We are going to divide. Basically, what we're going to do is we're going to look at the ratio of the next term in this type of series to its previous term. Now, if we do this for a geometric, right, we would get r, right? Because that's what common ratio tells us. But this is going to work for series that are not geometric as well, okay? We're going to take the limit of this as n goes to infinity, and this is going to equal L, some limit that we don't know. However, based on what that limit is, and you're going to notice it's an absolute value, so we're just dealing with a positive answer here. If that limit value is less than 1, just like with the common ratio in a geometric series, the series will converge. If L is bigger than 1, the series will diverge, and if L equals 1, it is inconclusive. We'll come back to this idea later on. Okay, so if we go back to opener C here, right, what we can do is do the ratio test, okay, for this series, all right? And so again, when we do the ratio test, we are doing this limit, okay? So that's what we're going to apply to this series right here, 1 over n factorial. So we must have limit notation in our work, something I'm definitely looking for in your work, okay? A sub n plus 1 is the next term in the series, so 1 over n plus 1 factorial divided by 1 over n. And so Very commonly, right, you're going to get some complex looking fraction thing, right? Go ahead and multiply by the reciprocal, okay? And the 1 over n factorial will become n factorial over 1. And now we can do a little bit of algebra here. Remember, n plus 1 factorial would be the number n plus 1 times n factorial. And so these n factorials would cancel. And so what that means is we would be left with the limit as n approaches infinity of 1 over n plus 1. And now, as n goes to infinity, that denominator is getting larger and larger, and so we would get 0 as our L value, right? So remember, this is L equals 0, and when L is less than 1, this converges. And so our series does converge, okay? Okay, so let's keep going, and the main thing we're doing in these notes is just practicing ratio tests, right? Writing out some interesting types of series, right? Applying ratio tests to them. So let's take a look at example 1. So from 0 to infinity, x plus 7 to the nth power. You're going to notice on my work here, I have the n highlighted in a lot of these because the thing I want you to realize is every time you see an n, when you're doing ratio tests, you have to replace it with an n plus 1. And we'll talk about what that looks like in more complicated looking series. Here, it shouldn't be too bad, okay? So limit as n approaches infinity, absolute value of x plus 7 to the n plus 1 over x plus 7 to the n. So again, this is the a sub n plus 1 term. This is the a sub n term here. And now we can apply some algebra to try to simplify this, right? When we are dividing, we subtract the exponents, so n minus n goes away, and then we get x plus 7 just to the first power. Now, something interesting that can happen with a ratio test question is that there's no n's left in the thing I'm taking the limit of, right? And so anything without an n is treated like a constant. You can basically factor it out. So this is kind of like if you're doing an integral in terms of x and you had another variable, you could bring that out, right? It's the same idea, okay? So there's no n's here. So basically, this just becomes absolute value of x plus 7. That is my L value, okay? So another way of kind of thinking of this, I didn't write it this way, but you could just take all of this, put it outside the limit, and then just have it be the limit of 1, right? And then the limit of 1 would be 1 times absolute value of x plus 7. Now, let's go back to the previous page. Ratio test, L has to be less than 1 in order to say the series converges, so we're going to take our L value, and we're going to set it to be less than 1. Okay, so L has to be less than 1 to converge. So absolute value of x plus 7 is less than 1. So a couple of things you can get asked this chapter, you know, like this question does right here, find the radius of convergence. The radius of convergence would just basically be what you get when you have like a 1x. So if this was like 3 times x plus 7, you would divide by 3, and your radius of convergence would be 1/3. But here, it's just an x already, so the radius of convergence is 1. This is an absolute value inequality. Let's go ahead and rewrite it. -1 less than x plus 7 less than 1. Subtract 7 on both sides, and so I get -8 to -6 as my interval of convergence. Okay, let's do another one. Example 2, find the radius of convergence. Now again, you're going to notice I have 3 n's highlighted here. Every single one of these needs to be rewritten, okay? So we're going to do ratio tests. So L equals limit as n approaches infinity. Replace all 3 of these n's with n plus 1. So let's start with that. So root n plus 1, x minus 1 to the n plus 1 power, and 3 over n plus 1, or excuse me, 3 to the n plus 1 power in the denominator. And then all of this is divided by the a sub n term, which is just whatever is inside the sigma notation to begin with, right? And so now it's just a whole lot of simplifying, right? Doing the algebra properly. First thing I'm going to do is rewrite this so that it is not multiplying, or excuse me, it is not dividing, it is instead multiplying by the reciprocal. And this is where copy and paste is your friend, just to kind of speed this up. Okay, and so now we have to try to simplify this. So we can be strategic with this, right? The first thing I notice is x minus 1 to the n plus 1, x minus 1 to the n. I can divide, subtract the exponents. Same thing with the bases of 3. subtract the exponents, okay? And so I get x minus 1 to the first in the numerator, 3 to the first in the denominator. These things I've highlighted because they do not have n's in them, which means I can put them outside of the limit. And so I can rewrite this as x minus 1 over 3. Now, technically, this is an absolute value for the x minus 1 because that's what's being factored, so absolute value of x minus 1. And now I'm left with the limit, absolute value of root n plus 1 over root n. And this is now going back to Calc A stuff, right? So what does that limit equal, right? That limit is just 1, right? Because this is like basically x to the 1/2 over x to the 1/2, right? Same power. And so no coefficients, right? The plus 1 doesn't matter as n goes to infinity. Okay, so that's just 1. And so remember, this is all the work to find L. So L equals 1/3 absolute value of x minus 1. We want this to be less than 1. And so first thing I'm going to do, multiply the 3 over, right? And so the radius of convergence would be 3 here, okay? And now I don't think the question asks for interval of convergence, but we could do that, right? We could write the inequality from -3 less than x minus 1, less than 3, add 1, and we would get -2 to 4, okay? So we could do that here, all right? But that's not what the question asks for. Okay, let's keep going. Example 3, this is where things get interesting. Find the radius of convergence. So again, every n, and now this is one where you got to really be careful, right? 2 times n. So then I'm replacing that n with an n plus 1. And so just exponent stuff here to be careful about, right? 2 times n plus 1, and then there's still a plus 1, okay? And then in the denominator, just whatever is in the sigma. And you're going to see me do the same first step on all of these. I'm going to rewrite this so that I'm multiplying by the reciprocal, okay? And so I went ahead and distributed the 2, so I get 2n plus 2 plus 1, so I get 2n plus 3, and now reverse the denominator, okay? And now, just like we talked about earlier, n plus 1 factorial is n plus 1 times n factorial, and so n factorials will cancel out, which is good for us. And then I can subtract the exponents on those x terms. And so limit as n approaches infinity of x squared over n plus 1. After subtracting those exponents, again, I'm highlighting the x squared here because it does not have an n, so I can bring that outside my limit. And so I get x squared times limit as n approaches infinity of 1 over n plus 1. Now, this limit, I think we should be able to do, right? That limit is just 0, right? Denominator keeps getting bigger, numerator does not. And so, no matter what x is, we're going to always get 0. So here's what this means. Remember, this is what L equals, and L has to be less than 1. So what this says is no matter what x you have, you're always getting 0 here, right? And so that means this always converges, and the radius of convergence is infinite, and the interval of convergence is -infinity to infinity. Okay. Okay, and our last one, example 4, is going to be kind of like the reverse case of this. Okay, again, we have 2 n's here. And so we get quantity n plus 1 times x, all of that to the n plus 1 power. And so this is over, again, the original thing in the sigma, quantity nx to the n power, okay? And so what I did here was I broke everything up. So this is a product to this power. So I put each of them getting the n plus 1 power. Same thing in the denominator. And so x to the n plus 1 over x to the n. We can go ahead and do that, right? And then I got a little tricky with this, right? N plus 1 to the n plus 1 power, right? When do I add an exponent? When I'm multiplying the same base. So n plus 1 to the n plus 1 to the first. And the reason I do that is now both of these are to the n power, so I'll be able to rewrite that. The x can come outside of the limit. Okay, so absolute value of x outside the limit, and I'll limit as n approaches infinity to the n plus 1 over n power. Okay, and this, let me just highlight this part here. This part right? Just the limit of that, I believe, is e. Someone should correct me if I'm wrong, but I believe that is e. Okay, but it doesn't matter because n is going to infinity, and so this whole thing is going to infinity. Okay, and so what we get here is that depending on what x is, if x is 0, then the whole thing is 0. Okay, right? But if x is not 0, well then L is infinite, right? So then again, L has to be less than 1 in order for this to converge. So this thing only converges when x is 0. It diverges everywhere else. Okay, so the radius of convergence is 0, and the interval of convergence, well, there is no interval. It's just the x value of 0. Okay. Okay, and so that is it for now. We will stop right here, and we will see you next time. Bye, everyone.